All right, so today we're focusing on reviewing how to draw Lewis structures, and I figured we'd start with the simplest case, which is for ionic compounds. And so here, for example, are lithium and fluorine. You can see if we draw their Lewis dot structures. Lithium, of course, has one valence electron, fluorine has 7, and so you can see that it's not a far jump to lithium giving up that one electron, fluorine taking it and becoming fluoride ion. And so I would draw them as lithium having lost that valence electron and having a positive charge, and fluoride having gained an electron and become negative. And you don't really see that too often. I think your book actually does, but a lot of times you just skip over that and get just to the good stuff. That's just a way to conceptualize what's happening when the ions form. To contrast that with how we do it when we have a molecular compound like carbon dioxide. And so what we're going to do is we're going to go through using carbon dioxide as an example. We're going to go through the steps. I'm going to remind you what those steps are, and we're going to practice it with several molecules. So be prepared to pause and work ones on your own here in a minute. All right, so first of all, the first step is to count up the total number of valence electrons, which for carbon dioxide, of course, carbon has 4 valence electrons and oxygen has 6 each, and there's 2 of them, so that gives us a total of 16 valence electrons that are out there available for bonding in CO2. So then the next step is we're going to sketch it and bond those guys, and typically, actually almost always for College Board, we're going to give you who's the central atom. They're going to write it in order or something like that, or give you part of the sketch. So you don't have to be able to determine the central atom, but just as a general rule of thumb, the more electronegative atoms or elements are going to be on the outside or terminal positions, and the less electronegative will be central. So here we go. We've got carbon in between these 2 oxygens. And notice that each of those bonds represents a pair of shared electrons, and so that cost me 4 electrons to bond these 2 together, and so now we have 12 more valence electrons to go. And then the next step is to give those terminal atoms their octet, which in this case required 6 each for 2 of the oxygen atoms, and so therefore that cost me 12, and so I don't have any left over. So step 4 is not going to apply in this case, but still make sure you record it and know to do it in the future. And that is, if there are any left over after bonding and giving the terminal their octet, you're going to put the remaining electrons on the central atom. So again, we didn't have any left over, so nobody goes on carbon at this point. So then I look at that carbon atom, because he's the only one without his octet yet, and I say, well, is there any way I can give carbon that octet? And of course, one way I can do that is to create multiple bonds. And so what I can do is I can use the electrons that each of those oxygens has and use those to create multiple bonds between the carbon and the oxygen. Then what I'm going to do after that is I'm going to evaluate the use. I'm going to evaluate, and what I mean by that is use either the octet rule and or formal charge to establish if there's a preferred structure or if there's a case of resonance. And so we're going to look at those last 2 steps in more detail here. So for example, to get multiple bonds to allow carbon to have his octet, I got a couple of choices, right? The easy choice is the first step, which is to take one of those pairs and make it a double bond between carbon and oxygen. But then that gives carbon 6 electrons, and so the question is, how do you get at the other 2? Well, of course, one option is for the other oxygen to contribute a pair of electrons and form another double bond, and it looks like this. But you also might say, well, wait a minute, couldn't it also just be one oxygen donates both extra pairs of electrons to the carbon? And that is a possible structure, right? That's an alternate structure that could be formed. Notice neither oxygen lost their octet, so we didn't mess anybody up there, and carbon did gain the octet both ways. So here's where we're going to do that evaluation to find out if one of these is preferred. And in class we were mentioning how, you might think just intuitively it makes sense in this case for the top structure to be preferred, just because there's not a difference in electronegativity between these two terminal atoms, right? There's not any reason to expect one of those oxygens to get the electrons around it more frequently than the other, like is shown in the second case. But we also have a formal way of demonstrating that and determining it, and it's what we call formal charge. And like many things in chemistry, I apologize, I don't make the term. I didn't come up with the name. But formal charge is not an actual charge. It's basically a calculation that talks about kind of what, kind of like oxidation states, right, where we assign what the charge would be if all of those bonds became ionic. But it's a calculation, and basically I say it is the number of valence electrons minus what I'll call the assigned electrons. And for me, assigned means all of the unshared electrons plus half of the ones in bonding. And so basically, most books and teachers will just write it out as one big long equation, that valence electrons minus all unshared minus half of the bonding. But I like to think of those two groups together as what I call assigned electrons. So let's use that to determine what the formal charge is in each element in each of these structures. And then we'll look at what the criteria are that we're going to use to compare the two structures. So if you look at the top structure, the first oxygen, of course, has 6 valence electrons, and it has those 2 unshared pairs, so we count all of those, so that's 4, and then each of those bonds represents 2 shared electrons, and so he gets half of those for a total of 6 electrons. And so 6 valence minus 6 assigned gives you a formal charge of 0. Carbon in the middle, of course, carbon has 4 valence electrons, and he gets one for each of those bonds because he gets half of the bonds associated with each of those. And so that's 4 assigned for a formal charge of 0. And then, of course, the right oxygen is just like the left oxygen with a formal charge of 0. In the bottom structure, the left oxygen, as you can see, only gets 5 assigned, right? There's the 2 that he has all of, and then 1 each of those bonds for a total of 5. So that gives a formal charge of positive 1. Carbon, of course, is again just half of those 4 bonding pairs, so 4 minus 4 is 0. And then the other oxygen has 6 all to itself, and then the 1 shared, giving him a formal charge of negative 1. And by the way, notice I write the positive and negative sign before the numeral, and that is because formal charge is not an actual charge. Just like oxidation states, we put the sign first, then the number, to contrast it with actual charges where we do the number first, then the sign. But then, so how do we decide between these two? Well, there's basically 2 main criteria that we're going to evaluate with formal charge. The first is we want the formal charges to be as small as possible in whole. So all of the formal charges to be as small as possible. Oh, by the way, I should mention that the total formal charge has to equal the total charge of the molecule. And so in this case, both of these are valid because they both add up to 0, and carbon dioxide doesn't have a net charge. And so neither of these is illegal by that. But then we want formal charges to be as small as possible. So in this case, the top row, 0, 0, 0, that's overall smaller than positive 1, 0, negative 1. Even though they both sum to 0, all zeros are as small as possible for the formal charges of every element. And obviously, I mean the absolute value of the charge, right? It doesn't matter that one's positive and one's negative, right? So that means that top structure is preferred. We say, well, what if we ended up with a situation where they were all the same? What if it was plus 1, 0, negative 1, and then there was another structure that was negative 1, 0, plus 1? Then we have to go to the second one, second criterion, which is a tie break, if you will. And that says that we want the most negative formal charge to be on the most electronegative element. So for example, we used the example in class of if this carbon was connected to a nitrogen and an oxygen, then we would want the oxygen to have the negative 1 formal charge and the nitrogen to have the positive 1 formal charge, since oxygen is more electronegative than nitrogen. So you see that occasionally, but usually we eliminate it by the first rule about how small the formal charges are in total. So therefore, this top structure is what we call a preferred structure. And so even though the second one is possible, it doesn't really happen. We get the first one. All right, so let's look at this one. Let's use this guy. Take a second to think about how you would name it, first of all. Good, because it's a molecular compound. We're going to have sulfur dioxide. And just make sure you didn't call it hyposulfite because this does not have a charge. So that was a little tricky, but if it had the -2 charge, then I would call it hyposulfite. But now, because it's not charged, that's just sulfur dioxide. So how would I draw that structure? Go ahead and pause the video and try and run it through the rules before you watch me do it. All right, so hopefully you took a swing at that. The first step I'm going to do is to add up the total valence electrons, which is, of course, 18. And as I draw it out and bond it, that's going to cost me 4, 2 per bond. And so now I'm left with 14. And then the next step says to give the terminal atoms their octet. So each of those oxygens is going to get 6 more. And that's going to cost me 12. And now I have 2 left. And so this time we do get to use that 5th step, and that is dump any remaining electrons on the central atom, which in this case is sulfur. All right, so then we look at it and we say, okay, well, everybody happy? Well, of course, we gave the terminal atoms their octet, but sulfur doesn't have an octet yet. And so now we're forced to say, well, how can we give sulfur its octet in a way that doesn't destroy oxygen's octet? And so, of course, one option would be for the oxygen on the right to contribute a pair of electrons to form a multiple bond with sulfur. And then the different option would be for the oxygen on the left to contribute a set of electrons to form the multiple bond between that oxygen and sulfur. And so my first question to you are these two different structures? Obviously, the one we saw last time with either 2 double bonds or a triple and a single, those were clearly different. Are these two structures different? Well, the answer is yes, they are fundamentally different. A different oxygen is contributing the pair of unshared electrons to contribute to make them shared to give the multiple bond. And so these are two different structures. So then anytime we have different structures, we have to ask the question, is there one that's preferred? And the way we're going to do that is we're going to assign formal charges. And of course, this oxygen gets a -1 because it has valence 6 and assigned 7. Sulfur has these 5 assigned to it, and so 6 minus 5 is +1. And of course, the oxygen on the right, 6 and 6 is 0. And then the bottom one is just reversed. We have 0, +1, -1. So there's not a difference in the total formal charges. They're all equally low. There's not a difference in who gets the -1. In both cases, oxygen gets the -1, and so it's not a case where there's somebody who's more electronegative that should have the negative. And so there's really no reason to prefer one of these over the other. And so when we have two structures that are fundamentally different, but one of them is not preferred, we call that resonance. And resonance means that it's basically a cross between the two. It's not, we show it with a double arrow like this, but I don't want that to confuse you. It does not mean that it switches back and forth from having the double bond on the right to having the double bond on the left. What it means is that that double bond is what we call delocalized. It's not on the right and it's not on the left. The answer to the question, is it on the right or is it on the left, is yes, it is. It's both. We call it delocalized. And so you can picture it as being, instead of a single bond on the left and a double bond on the right, or vice versa, you can picture it like both of these bonds are 1.5 bonds each. And so as a result, we find that if you were to try and break these bonds, you're going to get the same amount of energy required to break each of them. Because it's not a single bond and a double bond, it's somewhere in between. It's like a 1.5 bond. Same thing with its length. You know that single bonds are longer than double bonds. These two bonds will be the same length, and they will be shorter than a single bond and longer than a double bond. In other words, they're somewhere in between. And the reason they're somewhere in between is because that extra bond, that multiple bond, is delocalized. And so it's spread out between both of those pairs of atoms. So we call that a delocalized pi bond. We'll talk more about sigma and pi next class. But that is a delocalized double bond. And so that's what we call resonance. And again, it means that both of them are kind of halfway in between what they would be if it was not resonant. All right, so try this one yourself. All right, arsenic trifluoride. Of course, first up, how many total valence electrons? And I add them up and I get 26 there. And then I ask, okay, well then arsenic is first and fluorine is, of course, most electronegative, so it's terminal. So I spread them out. And by the way, we will talk next time about the actual geometry. So for right now, we're just kind of spreading them out on paper. We'll talk about what they look like in 3D next class. But that cost me 6 electrons, right? 2 per bond. And so now I've got 20 electrons left. That means the next stage is to give all the fluorine atoms their octet. That's going to cost me another 18, leaving me 2 electrons left. And of course, step 5 tells me dump them on the central. And so I dump them on arsenic. And as a result, arsenic managed to get its octet. So is there anything else I need to do? Are there any multiple bonds that need to be formed? And the answer, of course, is no. And so that was a simple one. But that's great, right? We like having a simple one every once in a while. All right, try this one on your own. Ammonium ion, which of course is NH4 with a positive 1 charge. Oh, and I advanced too fast. I gave you a little spoiler there. Notice it has 8 valence electrons because that plus charge, positive charge on this thing means that it lost one of those electrons. So it's only got 8. See if you can finish it up. All right, so here's the answer. Basically, as we draw it and bond it, that uses all 8 of them. I don't have anybody left to put on the middle, but that's okay because in having those 4 bonds, nitrogen managed to get its octet in the process. And by the way, I meant to mention this earlier. You notice when I said give all the terminal atoms their octet, I put octet in quotes. And the reason I did that is because of this example here. Obviously, hydrogen never has an octet, but 2 electrons for hydrogen is its octet. It's that stable full valence shells. So that's why I used quotes there. And then also notice, since this is an ion, we always put brackets around the Lewis structure and the charge up in the top right-hand corner. And that is an actual charge. All right, try this one. Carbonate ion. Pause it and try it yourself. Of course, the first step is figuring out what carbonate ion is, and that is, of course, CO3 with a -2 charge. And so when I count up the total number of valence electrons, I get 24. When I sketch it out with the carbon with the 3 oxygens around it, that costs me 6, and I'm left with 18. Well, you know, to give the terminal oxygens their octet, that's going to cost me 6 each for a total of 18, and that means I'm going to have 0 left. Now, I know that I started with a -2 charge, so I put the brackets and put a -2 charge. But notice, what I have to do? One of the oxygens had to contribute a pair of electrons to give a multiple bond, to give a double bond, in order for carbon to have its octet. Well, hopefully now you're just itching to say, well, something else might be going on here, right? Why did the bottom left oxygen get to be the one to contribute the extra electrons to form the multiple bond? Why didn't the top one do it? Or why didn't the bottom right one do it? Well, the answer, of course, is because all of them did and neither of them did. In other words, this is another example of resonance. That double bond is not between the carbon and the lower left oxygen, nor is it between the carbon and the lower right oxygen, nor is it between the carbon and the top oxygen. It's delocalized, it's spread out amongst the three of them, and so we see these resonance structures, and it means that all of those bonds are longer than a single bond, longer than a double bond, shorter than a single bond. It's like a bond and a third. And so it's going to be stronger than a single, but weaker than a double. But they're all three going to be the same. And again, this is a huge concept for College Board. That that delocalized bond means that all of these look the same. They're going to take the same amount of energy to break them, which is what we call their bond enthalpy. And we'll get to the actual quantity enthalpy later, but you'll hear that term, bond enthalpy. That's the amount of energy that we have to put in to break the bond, or the amount of energy we get out when we form it. And it's going to be the same for all three of these bonds. In other words, they're all identical. They're all between a single and a double. And then at the top, someone just asked, why can't we write it like this? And the reason it's preferred to write it in this triangular form is it clearly shows an arrow between all three structures. The one at the top doesn't clearly show A to C and C to A. So that's why this triangular shape is preferred when doing three resonance structures. But that's, it's a little nitpicky, but the double point-headed arrows are the most important thing. And understanding that those double-headed arrows do not mean it's transferring back and forth between them. It's literally all of them at the same time. So, and of course, that only makes sense because of our electron cloud model, that the electrons aren't in any one particular place. There's a probability of where they are, and that probability is spread out amongst those three oxygens. All right, which brings us to the last topic. We just briefly mentioned this idea of hybridization. I told class basically there's bad news and there's good news. The bad news is what I'm about to tell you is really an oversimplification, that it's much more complicated and involved than what I'm about to say. The good news is, from the College Board standpoint, and to do well on the exam, you don't have to understand it, you just have to be able to apply it. So I'm going to show you kind of what it is, give you the tip of the iceberg as far as what it actually is, but then we'll jump right to how is it applied to the College Board exam, and how can we get those easy points that they're going to give us just for understanding that it's kind of a thing and the general idea. So I drew methane, and methane is carbon bonded to 4 hydrogens. That's, of course, the structure that we would get if we followed those rules. Notice that carbon gets his octet, everybody's happy. And if I look at carbon alone, his valence electrons are 2 of them are in 2s, and then the other 2 are in 2p. And it looks like this, right? We draw this as its orbital diagram, right? But if I look at the picture on the left and this diagram on the right, you can see that it doesn't kind of add up. In other words, there's 4 identical bonds between carbon and hydrogen. And so which of those electrons in the picture of carbon, the diagram of carbon, is contributing to the bond with the top hydrogen, right? Which one's contributing to the bond of the right hydrogen? And you kind of want to say, well, the top one is the S, because when we first learned to draw Lewis dot diagrams in first year, you probably started at the top and worked your way around. But the reality is that's not at all what's happening. So those are identical, and so what carbon does is it hybridizes. And what that means is instead of having two s orbital electrons and two 2p orbital electrons, it divvies them up and it makes them occupy four identical orbitals, and we call those, we name them after who got broken up, right? So who got broken up? One of the s suborbitals got broken up, and then all three of the p suborbitals got broken up and mixed in together. And so we call this sp3 hybridization. Now again, it's really a little more complicated than this. I'm giving you kind of the general idea. We're not even worrying about shape and things like that. But here's what you really need to be able to do to grab the points. It might be sp3 if you have four bonding regions. If you look at the previous example we had, there were three bonding regions, and so you would expect that to be what we call sp2 hybridized. If there were only two bonding regions, like we saw in our original example with carbon and oxygen, that would be sp hybridized. And then if you had five bonding regions like this, you might be tempted to say sp4, but hold on, are there four different orientations for p orbitals? The answer is no. The most we can get for p is 3, so if we need more than 4, we have to go beyond sp3, and where are we going to go? To the d suborbitals. And so this, if there's 5 regions, we say that that's hybridized sp3d for a total of 5, right? 1 s, 3 p's, and 1 d. And notice, this is not going to be the first two rows, right? This is not going to be the first two periods. It's only going to be after we get to the third energy level that d suborbital is available. And so that's going to be something we have to watch out for there. But then, as we're going to be reminded when we review geometry next class, we can also have 6 bonding regions. And by the way, I know that is horrible as far as trying to visualize that. We'll do a better job next time. Class was getting to the end, so I was rushing. But if we need to have 6 bonding regions, then of course we need another D, and it becomes sp3d2. So again, as far as College Board's concerned, all you really need to know about hybridization is just a general idea that it's a mashup, if you will, of the different types of orbitals so that those bonds are identical, and being able to identify what type of hybridization it is, and it's solely by the number of bonding regions you have. So, all right, so I have posted the assignments for chapters 7 and 8, so you'll want to get on those in the next few days. Also, make sure you make a final, take a final mass of your reduction of copper by aluminum from the experiment from last class, and record that. After you do that, you can dispose of those in the trash, but do take a picture, please, of the final product. Obviously, most of them, you can see there's quite a bit of oxidation, and so we want a record of that, and you'll want to make sure you discuss that in your conclusion. All right, thanks so much.